Hello and welcome to the second part of my Blood VFX tutorial series. If you haven't watched the first part, I recommend you to do so first, because in that video I explain you my Houdini setup and how I store valuable data into the vertex colors of my fluid mesh. If you like, then you can also download the Houdini files and Unreal project if you'd like to follow along. Other than that, we can now get started to look into my Unreal project. Okay, so now we can import our static mesh to our Unreal project. So when we go to our Houdini project, and then under export, we go to the blood splash 08 geo, and then here I can import it. And then all you have to do is set the vertex color to replace, which will import its vertex color data, and then disable collision generation because we don't need it. Also, we don't need any light map UVs. And other than that, there's not much else, except that I also disabled creating materials or even importing textures. And that's it. So now you can import it. I'll just cancel out because I already imported them. And let me just select one of these three, if I can. There you go. And let me browse to those. And we can open it up, and we can also open up the material. And then I press this button here to assign the mesh to it. So now we're previewing from that mesh. Okay, so let's first start with the annoying part, and that's the time values. And that's actually because I'm calculating my own time values because I wanted to have a real-time preview within my window here. And of course, you can use your own time values, but I do it slightly differently. So let me first go to one of the effects, and then one that uses the fake VAT. So first of all, in the initialize, I set my lifetime. And then I also set a value called erode duration. And then here in this dynamic parameter, I set the lifetime to the duration, and I set the erode duration to the erode duration. So I'm basically feeding in those values. And then the duration, so the speed of my simulation, so the speed of how fast it goes from 0 to 1 is basically going to be my lifetime. So you can see that here, although here I'm also using the particle alpha color, and it might be confusing at the beginning, but if we go back to the initialized particle, I'm feeding the engine time into the vertex color alpha at the initialize, and this time is being paused and is also dilated, so it's basically the runtime. And it's the same as this, but I take a frame from the time and then I feed it into the time. And then when I subtract it from each other, I get a new runtime, so a time that starts from 0 when the particle was spawned. And then when I divide it with my duration, I get basically my normalized age. And why I do this inside is because also I wanted to offset the lifetime using the mass within the vertex alpha color. And that's why I wanted to have a bit more control on it. So here you can see it's called loop time. And when I were to enable use looping, you would see each piece burst separately. And I do this by basically multiplying the vertex alpha with the erode duration, and then I'm adding that offset, and then I'm fracturing it. So that's why all pieces have a separate offset in their time. But it's less interesting. And then when I disable it, this is more something that we desire, although it looks a bit more complicated. And first of all, this is now how we calculate the time, which is not as complicated. We do basically the same. We take the time that it was spawned, and then we subtract that from time, and then we divide to get the duration. So we map the time to 0 to 1. And then here I fracture it. So each time it looped, it goes back to 0, and then it goes to 1 and 0 and 1 and 0 and 1 endlessly. And this is the switch that I enabled, and here it says use debug. So when I were to disable it, it would use this one instead. But nothing's showing up. Well, that's because time is already gone past the number 1. And you might want to disable it when you use it for the particle, and in that case it would work, and the particle would kill after 2 seconds. So Actually, you could keep it enabled and it would still work. So even when it's looping here, the particle would have already died. But anyways, you can disable it if you want to. Okay, so now we have our sim time. And then we want to recalculate our erode time based on that sim time. So we have to work in percentages, if that makes sense. So first we want to find the time when we erode in percentage. So let's just say the duration is 2 seconds, and let's just say the erode duration is 0.5 seconds. So if I were to subtract it, now we would have 1.5. And then if I would divide 1.5 by 2, we get basically the percentage at when the erode starts. So that's 0.75, so at 75%. So now we have 0.75, and then if we invert it, we get the duration of the erode in percentage with the global duration. So now we know the 0.25 is basically the time until it gets to the end of the sim time. And then we multiply that with our erode duration offset. And then for the lower values, I remap that value because maybe the smaller droplets erode a little bit too soon. And you'll see that when I put it to 0, you see we have too many of these bigger pieces. So I remap those values, which gives us slightly nicer results. Okay, so we then multiply to find our erode amount. And then after we found the percentage, we then subtract it from our time. And now we offset the percentage time to the erode duration. And now we have to just map that back to 0 and 1 ranges. And how we can do this is, well, we have the erode amount. If we divide it with 1, if we divide 1 with that, and then use that result to multiply with this, we get back our erode duration that goes from 0 to 1 ranges. Okay, so that was the complicated part. Let's now dive into a more exciting part, and that's the world position offset. Okay, so let's first go to the beginning, and here we import the vertex colors, so the closest points. And we had to wiggle the y and the z values because in Houdini, the up axis is actually the y axis, but in real, this is actually the z axis. So as an optimization, what you could do is do the wiggling in Houdini so we can bypass this node. But now let's just move on. Then here I negate my vector, so it goes from 0, 1 to -1 and 1 ranges, simply by just subtracting with 0.5 and then multiplying with 2. And then I want to transform my vector from local to world space, because it could be that this effect is positioned anywhere else than just the center, with also some rotations applied to it. So therefore we need to transform our vector. And then here it comes. We grab our second UV coordinates and we take the x-axis because there we start the longest distance to. And then when we multiply our vector with that, we map it back to its initial form. So another optimization that you could do is perhaps use our bounding boxes, and then we can maybe even avoid having to use those. But anyways, then finally we can start rotating. And the first thing we wanted to do is we want to find the rotation axis, so this side vector. And luckily we have our forward vector from the closest point. So we take that vector and then we normalize it. And then if I take that vector and I take the cross product with the up axis, I find my side vector. So here, and then I normalize it. And then this one goes simply into my rotation axis. And then the pivot point is, well, our pivot. And of course, we want to transform that from local to world space. And then for each droplet, we want to rotate it, but we want to rotate it around that point. So we have to push back all the droplets back to the source. So we then can rotate it and then apply our offset afterwards. So that means we first had to subtract it from our world position. So here you can see the world position. And then I subtract from it our vector. So now all pieces are pushed back in. And yeah, then I can start rotating. So here I have my animation time. I recurve it. So it curves down over time it curves faster, and then I multiply with my strength, and then this goes into my rotation angle. And so now it's rotating, but of course I need to correct my normals. And it's slightly more easy. So again, I drop down another rotate about axis. There's also a method to use a single HLSL node, and then you can save on some constructions, but I don't want to waste my time here. And anyways, we feed in the rotation axis, the rotation angle. The pivot point is just 0 because this time we're not rotating positions, we are rotating vectors. And so therefore it can be 0, and then position is our vector or normal vector. And then we apply that offset to our vertex normal. And then I apply it by normalizing it. And then we have our corrected normals. But let's just first go back to our world position offset, because now here I am shifting the droplets based on that vector that we created. So here you can see after the 2 pins, here I multiply this with a value that I lerp from my animation time. And here I pow it with 0.5. So time goes fast in the beginning, and then bam, it goes slow, like you would expect a blood splash to look like, you see? And then I use that value that goes from 0 to 1 to lerp between the world position begin and world position end. And you can see here the world position begin is a negative value. So basically I'm pushing all the droplets behind their source, and I'm even masking them out. But I'll show you that later on. Anyways, I'm lerping in between, and then I multiply, and then I add that offset. So now you can see them shift out. And then additionally to all that, I'm also applying velocity. And you can see here I have my velocity. I've set it to minus 1.5, and then I multiply with my object scale so that it's relative to the object scale, of course. And then I use the alpha color to apply the weight to, so that the heavier pieces drop a little bit faster. And then here I take the animation time, I recurve it a bit, and then I multiply so that over time it drops. But I didn't really like the fact that the bigger pieces above were floating too much. And I was checking if the vector that we find from our vertex color, if it's pointing up simply by just taking the blue channel, and if that is pointing up, and then I remap the value a bit, and we can actually preview it. So give me a moment. Here you can see, so for those pieces, we then want to add a bit more gravity. So here you can see I add a multiplier, and then I multiply also with the gravity direction, and then I add that offset to it. So to show you real quick, I can strengthen this a bit more, and then you'll see the bigger pieces drop. But I like it better like this. Okay, so that's that. And then now finally, as the last thing for our world position offset, we are inflating our mesh so that the beginning of our sim looks a bit more like a round shape, similar to our VAT. So I'm inflating my mesh. Using the animation time, I can then recurve it, and then I lerp. So here you see over time, I remove the inflation, and then I multiply with that object scale, of course, so that it's local to it, and then I add that offset. And that's basically it for the world position offset. And then of course here I have some basic stuff going on, like the the color, the specular roughness, subsurface scattering, not really complicated stuff. So then here I wanted to add a bit more normal information into the mesh. And I'm doing this with triplanar coordinates. And you may remember I also created my own UVs, but I didn't really like the results. Maybe I was a bit too lazy, but actually I like this better. So yeah, I want to stick to it. And maybe there's also another approach. Maybe you could try to use cylindrical UV in wrapping, so that you only need to use one texture sample, because in the triplanar coordinates, yeah, we need to use 3 texture samples. Anyways, there are many courses about creating triplanar coordinates, so I won't go too deep into this. And then, yeah, we sample our texture, and then we blend this with our corrected normals. and then this one goes into my normal. But as some of you may have realized by now, when I search for tangent, here I disabled the tangent space normal. And you might be wondering, yeah, why do I do this? Well, it saves us a few instructions because my normals are in world space. And if this was enabled, what I could also do is then just transform this vector from world to tangent space and then enable the setting on our material, but it's actually a bit more expensive, so it's better to do it like this. Okay, so then finally we get to the last part, and actually it's also really interesting, I think, and that's the masking. And when I disconnect this here from the multiply, you can see the pieces here. Actually, let's just also connect this to the emissive. Just give me a quick moment, and then I'll do a breakdown. So yeah, here you can see it, the mask. And so what I needed to do is compare the world position after applying the offsets with the initial world position, so excluding the offsets. And then we can check with the dot product to see if this was facing in the opposite direction. And if it is, then we can, yeah, mask those out. But we had some issues with setting this to excluding material shader offset. So yeah, what we would basically do is then copy this one over like so, and we would have then one like this, and then this would be excluding shader offsets, and this one would be like so. But it doesn't work with opacity masks in Unreal. So yeah, you can learn from this now, really. And yeah, you might try it out yourself with some other settings. But anyways, what I did instead was I applied the offset manually. So I had to redo the math, or yeah, kind of repeat the math, kind of. But actually, it's better like that. So let me just first reconnect all my pins here. And you can see here, I apply the forward offset. And you may have not seen it. That's basically my vector, so the closest point vector. And then multiplied with the forward shift. And then here you can see it. And that's a named reroute, so you can create those, and you can set the name here and the color as well. It's really amazing. Anyways, I then subtract it from my world position offset, and then I take the dot product to find the opposite direction. And why I like doing it better is that imagine you have a blood splash that splashes up like so, and then gravity pulls it back down below its source, and it would mask it out. And we don't really want that. We want it to reveal when it's pushed out, and when it goes back below that source, we want to keep it visible. So that's actually why instead I'm using the forward vector, so the forward offset. And yeah, that's mostly it. The final part is just a Fresnel erode. So we take the camera vector and we take a dot product with the current normals. So you can see here, there you go. It may look a bit weird, and that's because the world position offset is not moving here, but it's applying it to the shader. But anyways, then we subtract with our erode, and yeah, that's it. Now we multiply this here, and we get our results. Although there's one thing to pay attention to, and that's I set here my opacity mask clip value to 0, and the initial value is 0.333. And what this does is it will check, okay, if the ingoing opacity is below that value, then set it to 0. But I want it actually to be on 0, so it's more accurate. But then I had the problem that if I stop previewing, and I had the problem that when because here it can be 0, it reveals itself again. So I had to offset a little bit with a small value to then be able to correct it. So therefore I had to say minus 0.1. Okay, and that's that for the material. Now we can move on to the next part, and that's creating the 2D sprites. But before we move on to the last part, I wanted to recommend you my Swoosh Effects course. And I can promise you that this is really an amazing course. It really offers you an amazing solution. Okay, so with that aside, we will now learn to create these Blot 2D sprites. And in specific, we will learn how to process the fluid mesh into these types of images. Alright, I'll see you in part 3. Cheers!